to poke you on this question regarding the relationship between water and electricity. Because I saw there you were talking about pumps. I'm just not sure how this entire process in terms of electricity consumption, bearing in mind the current crisis that we're facing in South Africa. Did you perhaps look into that aspect? Because I think for me sometimes, of which the research is quite good, it's solving the food security problem. On the other hand, we don't want to solve one problem and create another problem.
So that's where the way that farmers currently overcome that pumping issue comes to our benefits. So what they essentially do is have lower capacity pumps running most of the day to fill these tanks at higher levels to overcome the pumping issue, so that they've always got enough pressure for the irrigation. So by virtue of that, you can schedule your pumping times, because you're filling the tanks now for something that you might be using 2 days' time. So at least you can schedule around it for starters. And then secondly, that was the other benefit of using the VFDs with the power electronics that the previous speaker also spoke about. With the instead of all those losses associated with the valves, we are suddenly allowing the VFD to, with every percentage less that you're using, it's less power that's being consumed, and that brings the cost down for the user. The only problem then becoming that the power electronics involved have a high buy-in. So to purchase these systems to get them going in the first place, you're going to have to eat some costs, and that's where it hurts our more rural farmers again. So the first goal, I suppose, would be to also find a more cost-effective implementation for them.
Just a follow-up, Chief. I think for me it would be interesting to see the correlation, I accept your response. It's quite interesting. Just to see the correlation on the amount of water that can be purified or can be used for agricultural purposes relative to the amount of electricity used. And that will be quite an interesting study to look at.
So that was part of one thing I did forget to mention. Part of the reason filtration, apart from taking all the good minerals out of the water, is unattractive, is filter systems need to be maintained constantly. Then the filters need to be updated or replaced, cleaned. There's a lot of downtime associated with them. Cost and waste comes into that as well. And as I said, you're wasting all of these good minerals, having to dose them all back in at great cost, because you're suddenly buying vats of concentrate that you put your foot in and sort of melt off, and having the special control system just to mix them into the water. So, yeah.
Thank you so much. Is there any question?
Charles?
Yep. Okay, next presentation for economic area. Yes, with the title of Control Architecture for Multi-Step Pattern Recognition Algorithm in the Distributed Industrial System.
I'm sorry for my not good language. Excuse me. I will speak now about video analytics control systems. It's near software engineering than control, but maybe it may be interesting for implements in these ideas can be implements in control platforms in the hardware. And the video analytics process is usually when people think about video analytics, they usually do think about real time, but it's not true fully. Why? Because really, when people see into the object or into the action and observing, they see not milliseconds, but at least some seconds. And we can use in our systems this thing. Why? It's almost real time, predictable time. And if object is enough long, then we can observe and full time of object observation, but not at the moment of the frame in video capture. My system is specialized for industrial because sizes of objects and distances in real industry, in real factory is very long, very big, some kilometers, for example. 200 or 300 meters is not big for real video analytics system in industry. And when we work with these objects, we want to make digital twins for observing, supporting, and controlling the complex technological processes. If we work with one algorithm of ML and or two algorithms of ML, we can do it one by one as pipeline. But if objects are big and process more complex than one or two action, we have big problems with the time of calculations in ML. We work with technology process management, control of effects, and type completion. We want horizontal and vertical scalable for our solution because one server is not enough in any way. If we want more than one server, we have a multi-server architecture, and this area is too novice for now, for this time. Multi-server architecture are not described in a big number of books now. We have a limitation by time, as I said. The time should be predictable, not more than we can see the object in reality. And we need in high resolution image capture usual at least 10 gigabit per second because place of the cameras is not near the object. It may be very bad for cameras if they are near. Specific application is of applications is the composition of neural networks that calculation elementary actions or elementary objects properties for our video analytics system. Global structural solution is data prepare, then a main part, and then our runtime part, principal novice architecture with pipeline, not is that part is linear. It and I will speak about what's the difference in this work. Firstly, we can see that we want to work under one operation system. Not enough how many hardware we have. First idea is a shared memory of operational system. It can be used if hardware is not distributed. For example, some a year or two ago on Amazon OS we can try Tidal scale software that made some that combined some worker nodes and common operation system, as Linux as usual. it's not a good solution for video systems. I will say it later. But this idea is good because it can make possible to use very big shared memory. A lot of terabytes. 2, 3, 400 terabytes. And my pipeline middle server worked only over shared memory. When we have big cameras with big traffic, we can put this UDP traffic with mixed and put share memory, and then algorithms will use all these shared memory objects only 1 second. And algorithm, next idea is in classical pipeline, objects are strictly ordered. This is stage 0, stage 1, and then. But then in our pipeline, we do that. We take stage and replace it with state of algorithm. And the stage should be replaced to other node and put in only stage when we ask by network, or when as we ask over network, or as emits. We can work with events of stage, event of stages, instead of work the stage in this place. Then we can algorithm is usually Python. Python is not good for fast pipeline. If a pipeline we implement on low-level C, as a low-level C code, then we can take process, put it to other node, and take it in states only. The main communications is through the network, and 10 gigabit network is more than enough for this issue. This is the result of experiments. We take tube on the factory, about 6 meters. And 30 objects were observable. For 45 seconds we see objects, and 40 seconds between objects when each begins. And the result is this classical pipeline for 2.5 algorithms is 125 milliseconds, not enough, but 82 is enough. And that is idea for observable for this system, else system identification algorithm. It's not part of this speech, other presentation, and for the system. But this task was solved, and this meme describes this situation. It doesn't work why, and it works why. The problem that I say about the digital scale platform is it doesn't work with GPU, but all ML use GPU policy. And we start in St. Petersburg State University works with mixed these technologies and adapt it for this idea. Use GPU in this platform. Thank you for attention.
Thank you so
question.
Yeah, just out of interest, Chair, through you, I'm sorry. Why neural network? Why any other heuristical method? Because my understanding is that neural network, they require quite a number of huge data set to train and understand the architecture. But why neural network?
Why you use neural network?
Why we use it network? Because issues for communicate and for observable with network, with modern network, too fast for 1 gigabit is enough 1 gigabit, and a lot of cards with more than 1 ports available now, and they all resources for calculation in ML too slowly than calculation issues for ML too slowly than communication issues.
Thank you so much. Other question?
Thank you.
Thank you. Okay, next presentation for the Tobias with the title of development of an end-to-end tool chain for the AI assistant generation and optimization of operating strategy for hybrid electric vehicles.
So thank you very much, Ward, for the introduction. My name is Tobias Gera, and today I'm going to be talking about the development of an end-to-end tool chain for hybrid electric vehicles using AI assistant methods. So this is my agenda. First off, I want to start with the motivation. So why do we need an operation strategy? Why is it AI assistant? And why do we need hybrid electric vehicles? Then I'm going to give you a project overview, talk about the tool chain setup, show some of the optimization results, and summarize everything before I give an outlook to what we still plan to do and what can be optimized. Well, why hybrid electric vehicles? We see a strong push from internal combustion engine vehicles, as you see here, to battery electric vehicles. This makes a lot of sense in a lot of applications, but there are some cases where we need, for example, further range, or in general, further energy capacity. And I'm not only talking about passenger cars, but also commercial vehicles. How do hybrid electric vehicles work? You can see that basically down there you have your driver input, so what kind of state do you want to have, and then you need an operating strategy that will then split the torque that the driver wants or needs in this situation on the ICE and on the electric motor. And that torque split will be later on referred as torque split ratio. So if you see TSR, that's torque split ratio, and 1 means fully electric, and minus means we are recuperating, just as information. How do we create operating strategies, and what are the factors that influence them? First, we have to see what's our main focus. So do we want to focus on energy efficiency? Do we want to focus on reducing emissions? Or do we want to focus on, for example, performance only, like some hypercars do? Then we have to consider our boundary conditions. This is first our system, so the car, what is our state of charge, what are temperatures, etc. Also, we have boundary conditions regarding the outside, so the environment, our road, our traffic, our weather. So you can see, to summarize all of this, it takes a lot of development effort to create operating strategies for all those conditions, and not only regarding cost, but only regarding time, but also regarding time. So if you want to do that on the road in a live environment, it's very costly, and it makes sense to create those operating strategies in a simulated environment, just to cut down cost and reduce time. This is like short project overview. So our research has been created in a public funded project, and our main focus was to create a tool chain to create and optimize those operating strategies. You can see this tool chain here. It's basically starting with a car and an engine. We will create emission models. With those emission models, we will then go into a vehicle simulation, close the circle with real-time hardware, and then test our strategies. And then, as always, iterate. And part of that project I'm going to present today, and this is presented in paper. Because we want to do operating strategies for a hybrid electric vehicle, this is exactly where we started. So we took a BMW 530e, which is a P2 hybrid, and equipped it with additional technology and measurement devices. As you can see here, this is a portable emission measurement system. We have some GPS stuff, and we have OBD loggers to just log some engine and GPS data from the car. But we not only did this on the road, but we also did this on the test bench. So here you can see our test bench engine. It's basically the same engine that's in the cars, so the same combustion engine. We did this because we wanted to focus on emissions. And in the lab and on the test bench, we just have the advantage that we have a controlled environment, so temperatures and everything are the same. We can control all that stuff. And we just can use more dedicated hardware, so we can add more sensors. As you can see on the right, we couldn't do that on the full vehicle because it was a leasing vehicle, so they would not have been happy if we filled a lot of holes in it. And we just could also use more dedicated emission measurement technology with higher frequencies. Here you can see just an example for a measurement. So this is, for example, NOx over time. And the way we have done that is we have taken logs on the car, so we can make sure that we are facing real driving situations. We took those and copied it basically on the test bench, so exactly the same behavior on the car. The engine had on the road in the car, we could reproduce on our test bench. Now, what do we do with those measurements? With those emission measurements, we can create emission models, and we tried different ways. So we tried physical modeling, the classical stuff, and we also tried machine learning algorithms, starting from shallow learning algorithms like random forest or NARS to the deep learning stuff. Those are basically our inputs. They are just speed, torque, and air-fuel ratio. We wanted to keep the inputs very simple because for an operating strategy, it makes sense to have inputs that, of course, influence the outputs. Otherwise, it makes no sense at all. And you want to be able to predict those values in the future because that's basically essential to see how you can react with the car in the end. On the output side, we have several gauges, engine emissions, so nitrogen oxide, CO2, carbon oxide, unburned hydrocarbons, and so on. Now, this is just basically what we did. So we took those basic models, we had our training data, which was like over 20 hours of real driving on the test bench, on real driving conditions. We did our model training, and hyperparameter optimization. So the models got a different shape. Of course, it's way different than what you can see here. We took our test data and did our model testing and performance evaluation. With our emission models and more data, we were able to basically do a digital twin of the BMW 530e in space ASM, so we were able to simulate the car, and now we have everything basically in the simulated world, and we are able to speed up the progress. We then tried several optimization methods, starting from model predictive control, but also reinforcement learning, what you can see here. Basically, what is reinforcement learning? We have our agent, we have our environment, and our agent is able to take several actions in the environment. The agent also observes how our states changed, and it's then either penalized or gets a reward if he does good. This is just to get a short overview. The action it could take was adapting the torque split ratio, so just change how many torque we get from the internal combustion engine or from the electric motor, if we recuperate or whatever. And the observations are basically those that you see here on the top. Yeah, and penalties you can see here. Of course, we wanted to stay in our state of charge boundary because it would be unfair to use all the battery and you cannot compare everything. And this was our main goal, so we wanted to reduce emissions. So now how do we close the loop? Because basically now we have everything in the virtual world, but we also want to verify that in the real world. Our system is very complicated. You can see basically the internal combustion engine on the test bench in the middle and just all the stuff outside of it that has to work and that has to be connected to get all this working. Today I want to just focus on the core part, which is basically what you can see here. This is our engine test bench, so we have an automation system that basically controls everything, like gas pedal, has some security features, and so on. In our rapid control prototyping system, we have our vehicle model, our environment, and our driver model. And we also have a machine learning deployment system where we can run our emission models and our operating strategy. So basically, we have our car here driving around in the virtual world. We have our emission models and operating strategy that tell the virtual driver what he should do. And we then give those signals, basically the gas pedal, to the engine test bench to see what the ICE does. The electric motor is also simulated. And we get feedback from the engine test bench regarding emission measurements and stuff like that. So by doing that, we were able to verify our models. This is just a final look at some optimization results. We can see basically our basic hybrid electric vehicle agent in red and our emission reduction agent in green. On the top, you can just see a velocity profile in that situation. This is the torque split ratio. As said, 1 means fully electric, minus means recuperating, and 0 means 0 torque. And on the bottom, what you can see here is called global warming potential. So basically, we have like all those emission values that you see, emission parameters that you saw before. And with the GWT, it's some kind of CO2 equivalency factor, which just makes sense to combine all those emissions into one combined value because it's easier to set optimization target by doing that. And you can see here that the torque split ratio is completely different regarding those two agents. And what that does is, what you can see here, we can see a decrease in global warming potential by basically very fast reactions that cut those peaks that might come from strong acceleration phases, for example, from the ICE. Just to summarize everything, we created our end-to-end tool chain and used machine learning models at several stages. As you can see here, to model the vehicle, to model the emissions, to model the vehicle, and also to do the optimization. But there's still a lot of knowledge and special knowledge needed. For example, here you need all the knowledge to basically define what kind of cycles you want to run. You need a lot of machine learning knowledge to set up the models, how should they look, optimize hyperparameters, etc. So there's still work to do, and what we want to do next is basically create something that is only reliant on machine learning, and we want to automate the complete process. So basically we have our engine test bench and we have data acquisition measurements. We then want to automate it, do the data processing, so split it into training and test data, create a model out of scratch, do some validation, and based on our optimized, on our model errors, we want to do an optimized measurement program, go back to the engine test bench, run that program automatically, and then just iterate, and rebuild our neural network. And hopefully we can talk about this next year. Yeah, so just thank you to our funding partner, and thank you to our project partners, which you can see here. And thank you very much for your attention.
Thank you so much. Is there any question?
Yeah, is it possible to compare how the machine learning operating strategy compares to traditional manually designed operating strategy? Is it, yeah.
Yeah, that's possible. For example, that last agent was basically the standard agent, more or less focusing on energy efficiency. So of course, the emission reduction agent is trained on a different target, but it's way better regarding emission reduction than it lacks regarding energy efficiency. So basically, of course, you sometimes have to do a trade-off, but you gain more with this than you lose on the other side.
So the green line there, the machine learning agent?
Yeah.
And the red one is also with machine learning, or that's
No.
Okay.
That's the standard one.
Thank you so much.
Thank you.
It's a term this was in course. I don't Prof. Bangakhuluma yini lapha?
It's now. It's business.
Hello everyone, this is my presentation. My name is Ray. I'm a PhD student from the Stellenbosch University, and our research is about the comparison of the sensorless control methods for the PMS and for the shift proportion application.
Can I chair on your behalf?
Sorry?
Can I chair on your behalf?
Yes, why not? Yes, my outline is about the introduction of the PMS and sensorless control. After that, the model description for the 500 PM machine for chip proportion and model of the profile load for the chip proportion, and the focus of our research about the sensorless control that we use for this application, and the comparison of the observer for detect the position and speed for the chip proportion and simulation and results. The PMSM machine is very useful and very competitive in the market in terms of the speed and maintenance and torque and ripple and so on. So it's very useful for this application in terms of the cost compared to the other machine, something induction machine or stepper motor or something like that. In this slide, you can see some application that we can use PMSM machine in the larger scale, medium scale, and also the small scale. We can see the wave energy and wind turbine, and for the small scale, for the focusing of the camera or the lens, and for the medium scale, electric vehicle, it's very common. This slide shows the structure of our machine that we use for our research. This is for the 5 megawatt PM SM machine. And you can see the rated power, rated speed, and the voltage it used for this application. As you can see, all schematic of the chip proportion is the onboard power. After that, this part is for the control system that we use, and we focus on this part. And this is the load for the chip proportion. And this is the whole block diagram of the chip proportion for the electric system on the chip proportion. And this is like we simulate a real chip for the 5 megawatt application. As you can see, the diameter of the propeller is 3.5 meter, and the weight of the vessel, and so on. And the next block diagram shows the simulation of the propeller load that we use for the simulation. This slide explains about the equation for the PMSM machine. This equation exactly same for the all of PMSM machine that we can use, and we can simulate the all of PM machine. But the only difference in terms of the loss, vibration, or something like that. But the focus is on the our research, sensorless control. Sensorless control is divided two parts. One part is for high speed range, and the other part is the low speed, zero speed, and medium speed. For the zero speed, most of the researchers use the signal injection and FPV base, and for the high speed or medium speed, it's very common use the model base with open loop and closed loop, and the observer that we use. Extended Kalman filter, model reference, a sliding mode observer, and unifier. But the most common observer that the researcher this time is used is the sliding mode because of the advantage of this observer. And these days is very active. The most researchers use combination method. For the start, we can use the sensorless control with salience device, signal injection, and after that, for changing the speed, we can use the model-based model. In this paper, or in this research, we use the sliding mode observer and comparison with the other observer for the high speed and medium speed. As you can see, this block diagram shows how we can control the machine. At the first, we measure the current. After that, we can transfer the ABC to the part or clock transformation. After that, based on the part or current transformation, we can estimate the position and speed of the machine. After that, for the tuning the machine for our speed, we use the two regular current. After that, we can insert the current to the SVPWM or space vector force contribution to the inverter or the converter, and we can control the machine. In this part, our focus is on the rotor position, and we compare four observers together, and we want to find which observer is useful for the chip proportion application. Because based on the application, the observer has a various behavior. So we want to find the best observer for the chip proportion in the high power system. This block diagram is for model reference that we use, and the other is for extended Kalman filter. As you can see, we measure the current and voltage, both of them, for the extended Kalman filter and model reference. And the next slide, you can see the lunar vector observer and a sliding mode observer. The comparison for observer for the ship proportion in high power application. But our focus on the sliding mode. As I said, the sliding mode is very active observer in this day, and most of the researcher wants to develop this observer for the various applications. So we use the fast terminal sliding mode observer. All of the observer have an advantage and disadvantage, but for the sliding mode, the chattering problem is very important. We want to decrease this part of the tracking of position and speed. So we defined a new function for the sliding mode that with this function we can compensate this chattering problem, and we can to achieve the very fast convergence. Because of that, we call that the fast terminal, because of the fast convergence. And the next slide, you can see the tracking speed of the all-of observer. In the real, the comparison of the position estimation versus time, rotor position. The blue one is for the sliding mode, and the other color for the other observer. As you can see, the sliding mode in the rotor position, it's has not good performance, but it's the only disadvantage for sliding. But for next slide, this is the error for the comparison, and in this slide for the estimation, the observer. As you can see, the sliding mode has a good performance in terms of the estimation, compared with the real speed of the propeller load. And for the model reference, you can see a lot of interrupt of the estimation. But the big advantage for the sliding mode is current, because current can make the machine hot, and in terms of the temperature of the machine, for the high power is very important. Because of that, the current is very important to control, to decrease the type of the current. As you can see, the current is much better than in terms of the temperature compared to the other observers. And the position. The position estimation for the sliding mode is much better than the other. The scale is different if you want to see. The sliding mode has a better performance compared to the other observer. And this is the electromagnetic torque for the machine. Also in this slide, the sliding mode has a good performance compared to the other observer. And this table shows the advantage and disadvantage of the all-of observer that we comparison, and we figure out the sliding mode with our development as a better performance compared to the other observer. So in this paper, we found that the sliding mode can be improved for the high power application. Not only for the ship propulsion, but also for the other application like the wind turbine or something like that. For the simulation and conclusion, this observer can to use for the wide speed range, even in the 0 to high speed. And also this observer can estimate the negative speed, because for the ship propulsion we need to use the vice versa speed and positive or negative speed. And this is our research that we have in this year about the sensorless control for the normal machine, vernier machine, and PM machine, and also for the dual click phase. Thank you so much for your attention.
Questions, please? In the absence of questions?
Thank you so much. Yes, I think the session is going on to take.
There's going to be group photos outside of the hotel.
Thank you. So the group photos just go right out the door and then it's past the restaurant and outside. Okay, now take pictures.
Authentication, two-factor authentication ti wà tipẹ́tipẹ́tipẹ́. Nǹkan tí ẹ̀kan náà sọ náà nìyẹn pé all this ṣọ́ ẹ̀jẹ̀ drop number pé group pé ilẹ̀ number ẹ̀ because me kó tó lè hàn number báyìí á tún lẹ́kọ̀ọ́ àwọn authentication ó tẹ̀ tó lè hàn sí ẹgbẹ́ wọ́n máa ti ní sí kan máa sẹ́yìn lójú ìfúnná ọ̀dà authentication kí á tẹ́ ẹ̀ máa ń gbé ìwé lọ́dún ìbáyìí. No, but nǹkan tí èèyàn jà nǹkan tí èèyàn tẹ̀lé pọ̀ ní pé tó bá ti jẹ nọ́mbà àkáǹtì ìwé kí ẹ ní nọ́mbà orúkọ ẹni yẹn kì lónìí tó kọ̀wé bọ̀ tó bá ti lè jẹ́ pé bá mi sẹ́yìn sọ́dọ̀ nǹkan ló lè kú dára àti ó lè ní bó ṣe sọ́ọ̀tì nǹkan tó ẹgbẹ́ ti fún ìyá. Ó lágbára owó lè ju owó olóòrùn lè ju owó lè yẹ kí ṣe lọ́wọ́ ó ti dáka ti lò ìdú dáka ti bá láì dé no try all right oh yes yes ìdílé ìgbà pọ̀ sí Hey, are you guys leaving now? Okay, okay.